This video, implementing a multi-layer perceptron using vectors in C++, is a follow-up to our earlier video on implementing a multi-layer perceptron in C++, which can be found at this link. In this implementation, we use fixed size arrays for clarity of presentation, and the array names match mathematical symbols used in the discussion. In practice, however, you may prefer dynamic data structures such as vectors, which allow users to enter network parameters more flexibly. This figure shows a multi-layer perceptron. The layers are indexed by L from 0 to capital L. In this example, the network has 3 hidden layers, so capital L equals 4. This is the implementation. We use the same variable names as before. So we have N1 inputs plus bias, and K is the number of outputs, so these are the default values, and W is the Weiss vector. It is 3-dimensional. Z, the logic, is 2-dimensional, and A, the value of a neuron, is 2-dimensional, and Y is 1 dimension, is the predicted output, and sizes 1-dimensional vector stores the sizes of the layers. It has 3 constructors. This is the default constructor. This constructor has 1 input parameter, the learning rate, and this one, besides learning rate, it has parameters N1, the number of input values, and K, the output size, and also this vector contains the hidden layer sizes. So these are the functions we used before. Forward, backward train, and input size returns the input size of MLP, that's N1, and output size returns the output size of the MLP, that's K, and save weights and param. Besides saving the weights, we also save some parameters like N1 and K. And read weights and param is to read the weights back and also the parameters. Because we use vectors in our implementation, we need 2 external functions to set the capacities of the vectors once the sizes of the layers are defined. So in this function, set YC capacity, we set the capacity of Y, Z, and A. So we use the member function of a vector reserve, to set the capacity of a 1-dimensional vector. And because C is 2-dimensional, so first we use reserve to set the number of rows that C has, that's L plus 1. And then for each row, we define the number of columns. So again, we use reserve, the size is L. And we use pushback to push this row into C. Now, the function move here does not actually move anything by itself. Instead, it just cuts its argument into an R value reference, which allows the object to be moved from when passed to a function like pushback. So with this move, the function works faster. Without, then the row will be duplicated. It takes more time to do it. So we do the same thing for A. This will define the capacity of the vector A. And we also need to set the capacity of the weight vector W, which is three-dimensional. So we use the same trick, so we need to do it 3 times. And the external function initialize ways is to initialize W with some random weights. And so this is the default constructor, and constructor with one input parameter. Others will use the default parameters. Again, so it's set the weight capacity, set YCA capacity, and then inertial rates. And then with this N1K and hidden as input parameters, so we set the corresponding variables to the input values. Again, we create, first define the capacities and initialize rates. And other functions are the same as before. And an input size returns N1, output size returns K, and so save weights and param. So we save the weights and some parameters L, and also the sizes, and with the weights, need to read those parameter back, and then use those parameters to set the capacity. This is the testing routine. We use the same lim game routine to do the test. This is the main. So if we just execute the program, then we'll display a message telling the user how to use this program. So at least we need to enter one input parameter, that's the learning rate. And we use A to F to convert this argument to the actual value learning rate. If it is larger than 0, and we don't have other arguments, then we use this constructor to construct an MLP object. So we only have the learning rate as the input parameter. If we have more, then we construct the object with other parameters, N1, and also the hidden layer sizes. So the hidden layer sizes could be the input or the default parameters. If the learning rate is not larger than 0, we just create an MVP object using the default constructor and with the weights from this file. And here we with the input size and output size back to use this to construct the database. And we use this database to do the test. If learning rate is larger than 0, then we need to do the training. Otherwise, we just use the ways from the file, okay, to do the test. So again, if the move from the LIM program is not the same as that from the MLP, okay, then we save it, and we save this to the I, okay, put that into div, okay. And after we have iterated through all the possible I, and then we display the different I's. Okay. So that's the testing routine. We have copied the files to this directory. So this is the header. The program. The testing routine. So all these are the same as you have seen on the website. Okay. So let's compile this. G++ -O. Suppose we call the executable to be lim MLP. So we compile it, and suppose we just execute it, and displays a message telling us how to use it. So we need the learning rate. Suppose we set the learning rate to be 0.5. Okay. So it takes this as input and begins the training. Okay, and then in the checking, so out of 254, only have 3 different. And now, if we input this as 0, then we'll. Oh, sorry. Let's see this. Okay, now it saves these weights. Okay. So this is the weight it has saved. Okay, and some other parameters, learning rate. And suppose we input 0 here, then we'll get the weights from the file, okay, without training. So, but we get the same results. Okay, as this. Okay. So now we can also input other parameters. Say the n inputs, so suppose it is 9, and then the n outputs, so there's 7, okay. And then the hidden layers, suppose we use 15, okay, 15, okay, 3 layers or 15. So again, it begins to train it, and so we get the same result as before. And so if you use 0, then we'll get the weights from the file. Okay. And of course, you can use the different hidden layer sizes. Okay. Suppose we changed it to 16. Okay. And so the difference in size is only 1. Okay. So again, if you use 0 here, so you get the same result. Okay. So you, with this vector implementation, you can experiment the MLP with different parameters, say different hidden sizes, different inputs, different learning rates. So it is a lot more flexible. Okay, well, yeah, thank you for watching, and I will see you in the next video.